Fine, I'll repeat what we have discussed in the class. Uh, Apart from all this all about. And for the students who have joined from Madhu ma'am's batch, we'll have certain videos shared with you based on the properties of regular languages. Fine. So let me go ahead with the right quotient part. It is right quotient of regular languages where two regular languages will take L1 and L2 be any regular language, and the right quotient of L1 slash L2, which means slash is the operator which represents the right quotient of two languages. The right quotient of L1 slash L2 will be a set of strings X, where you try to find a set of strings from the first set of language L1, which can be divided into two parts, X and Y. Any string which is at least some strings which are represented in L1 can be divided into X and Y, where Y is a string which is represented in L2, which and the other of that string xy is considered as L1 slash L2. That is what they mean by this definition. Just for our understanding, L1 slash L2 is X, where XY is a part of L1 and Y is a part of L2. Fine. Now, for example, L1 has a string AABB, whereas L2 has a string BB. One second. L1 has a string, L2 has a string BB. Now, if you just have a look at it, AA can be considered as X based on your definition. I'll just have the definition to be pasted here so that it gives us a better understanding. Now, what happens here? Here the string which is represented in L1 is is divided into two substrings. One is X and the other one is Y. X is considered as AA and Y is considered as BB. And you try to find the substring BB in L2. That is why we have marked it in red. These two are there. In that case, L1 slash L2 will be the first part, which you call it as uh, the right quotient of L1 slash L2. Now, how do you really find the L1 slash L2 for any given problem? For example, let us go ahead with L1 as A closure, B AA closure, and L2 as AB closure. Now, for L1, let us draw the diagram first. For L1, let us draw we have a transition on B from Q0 to Q1. Q1 to Q2 is on A, and the next A closure is another transition on Q2. Now, Q3 is a trap state. Q3 is a trap state or a dead state. Now, what happens? We are supposed to find the L1 slash L2. How do I find L1 slash L2? Given L1's diagram, we'll try to given L1's diagram, we'll just try to figure out given L1's diagram, we'll try to figure out the new final states. That is what it means. We'll try to figure out the new final states. So what happens? We'll try to generate the strings on L2. So the strings on L2 for AB closure can be A, AB, ABB, and so on. So we'll start with Q0. Q0 on A reaches Q0 alone. If you read Q0 on AB, it reaches Q1. Q0 and Q1 are not final states. What about ABB? It leads to the trap state. So this Q0 is not an final state. Now we'll take from Q1. Q1 on A reaches Q2. At least one string has to reach the final state from any given states of L2. L1. So Q1 on A moves to Q2. So Q1 acts as the new final state. What about Q3? From Q3, we cannot move anywhere, and therefore this is a trap state. This is not a final state. Q2 on A also reaches Q2 again, the final state. So this is also a new final state. In other words, in our technical terms, we'll take the language generated from Q0 with Q0 as the initial state, intersection with language Q2, L2, it's a null set. When you take the words which can be generated from Q1 and the words generated from L2, you have a string in common to these two, which is A. And similarly, for a Q2, it's also A. So the new final states will be Q1 and Q2. Having said that, your new final state is this part. Q1 is a final state, Q2 is the final state, Q1, Q0, and Q3 are non-final states. Fine. How do I solve it? You try to the step one. You try to draw the finite automata for L1. Drawing trap state is not a must. Just try to draw a diagram for L1. Then generate, populate the strings for L. That is what we have done here. Okay, we have drawn the diagram for L1. We have populated access. Final. So that is what we have done here. You've tried to
Ma'am,
find
one of my
the
friend is
these
waiting to
Q1 and
join.
Q2 are final states. So those two are considered. Yeah, one second. Now, if you can generate a regular expression for L1 slash L2, do it, or else just stop it to the diagram of L1 slash L2. There is no need to write a regular expression. If you can, do it. If you cannot, stop it with the diagram. Okay, so what have I done here is here it is A closure B is the first regular expression, and A closure B A closure is the second regular expression. We have tried to combine it and say it is A closure B A closure. Fine. That is, we'll take one more case here. We'll take the next example where you say L1 is A per N B per M, where N is greater than or equal to 1, which means there has to be one occurrence of A, which is mandatory, and then M greater than or equal to 0, which means 0 occurrence of B is also allowed. Union BA. So two different languages are combined. And then L2 is B per M greater than or equal to 1, you are supposed to find what is L1 slash L2. So we'll draw the diagram for uh, the first part, A per N, B per M, N greater than or equal to 1, and M greater than or equal to 0. So what are we supposed to do? 1A is mandatory. So from Q0, you read 1A, you move to the first final state, and after which I can have any number of A's. So A per N is provided over here. And the A per N, where N is greater than 1 on the first A, you move to a final state, and after which I can have any number of final states. How many number of B's are allowed? 0 B's are allowed, any number of B's are allowed. So if 0 B's are allowed, Q1 acts as the final state. If more than 1 B is allowed, Q2 acts as the final state. And then what about the next part? The next part you say it is union BA. So where have we drawn? From Q0 on B it moves to Q3. From Q3 on A it moves to Q4, the next final state. So you have three final states, Q1, Q2, and Q4. Q5 is the trap state. Now, having drawn this, what are we supposed to do? We have to find uh, L1 slash L2, where L2 is B per M greater than or equal to 1, which means single B is allowed, multiple B is allowed. Now, if you just look at it, Q naught, you read B, you will reach only Q3 and not the final state. So Q naught will not act as a new final state. We are supposed to identify the new final states, for which you have to consider the strings which are generated by L2. The strings which are generated by L2 will be B, 2Bs, 3Bs, and so on. The reason is it represents B per M, where M is greater than or equal to 1. Okay, and from Q naught, you have only transition on B to Q3, which is a non-final state. Therefore Q naught will not act as a final state. Now we'll take Q1 on B, it moves to Q2. So it reaches a final state. So Q1 acts as a new final state. What about Q2? Q2 on B leads to Q2. It again acts as a new final state. What about Q3? Q3 on B, it moves to a trap state. So this is not a final state. What about Q4? Q4 on B moves to a trap state. So this is not a final state. So which part, all these Q1, Q5, Q4 are not final states. The final states are Q1 and Q2. Fine. And therefore the end result will be this part alone, which is A closure, and then B closure. Or the other way around is A per N, B per M, the first part of L1, N greater than or equal to 1 and M greater than or equal to 0. We'll have one more example before we move on to the next one. Fine. So you have here L1, which is A closure, A closure. We'll try to find out how this particular thing works. Fine, we'll just try to draw the diagram for A closure, A closure. So Q naught, B, A, and then A closure. Let this Q naught, okay, let this Q naught act as the initial state, and Q naught will have a self loop on A to accommodate the A closure, and then from Q naught you have a transition on B to Q1. Q1 we have a transition on A to Q2, and Q2 you have a self loop on A to accommodate the last A closure, and Q2 acts as the final state. Fine, we haven't drawn the trap state, we have just considered this particular diagram. What about L2? L2 has these strings, the strings given below to be generated. It is A, B, A closure. So if A closure is an empty string, you will have A, B, A, B, A, B, A, and so on. Now, how do I define it? Now the question is, from Q naught on A, B, will I reach the final state? So given these informations, just let us try to figure out from Q naught on reading AB, you will not reach, you will reach only Q1. You will never reach the final state. So Q naught will not act as the new final state. What about Q1? Q1, so I will, on taking the first string, it's A, B, you have only A, so that is ruled out. Q2 is also ruled out. We'll take the second string here, A, B, A. Q naught on A goes to Q naught, B and Q1, and on A it moves to Q2. So Q naught acts as the new final state. One second. Fine. Now, my question is, given this diagram, which are the new final states which represents L1 slash L2? Can you put it onto the chat box, please? Given the diagram, which are the new final states? Can I have it on the chat box, please? You have the diagram L1 which is displayed. You have the strings which are displayed. Now tell me which of the states Q1, Q2 and Q0 acts as the new final state. Okay. Okay, the answer is Q naught. The reason is when you take the first string doesn't satisfy any of. Thank you, Maf. Thank you for your response. The first string doesn't satisfy any of the condition, but when you take the second string from Q naught, you can read A, which reaches Q naught itself, and then on B it moves to Q1, and it reaches the final state on reading A. So Q naught acts as the new final state. What about Q1? Q1 on A, you can reach the final state, but you cannot read B. There is no B's transition after Q2, and therefore Q1 is not in final state. Q2 also has the same explanation, therefore Q2 is also not in final state. Now the only final state which you can consider while L1 slash L2 is Q0. So what can be the regular expression for L1 slash L2? What is the regular expression for L1 slash L2? Can I have some guesses from your end? We have decided that Q naught is the final state. So what will be the regular expression for L1 slash L2? Okay, we'll define uh, Q naught. We'll define L1 slash L2. This Q naught state acts as a final state, and Q2 is non-final. Okay. Now tell me, what is the regular expression which represents Q naught as the initial state and the final state? Tell me what is the valid regular expression from the given diagram. Okay. Any other options? What is the regular expression for the given diagram? Can I have answers, please? Since only one has answered, we'll go for a poll. Okay. Now let me stop presenting. The question is the diagram which is given above. You have the poll over there. You can select the options. I'll give you another 2 seconds to finish it off. We'll close. You have only 27 students who have responded. Is there anyone willing to respond in another 2 minutes? Okay. I have closed it. Now, the question is which one is correct? As for this diagram, Q naught is the final state. Okay. And after which you have Q1 and Q2. Now, if I reach Q1, there is no way I have to reach uh, Q naught. And if I reach Q2, there is no way I'll end up in Q naught again. So this Q1 and Q2 will act as a trap state for the given diagram. And therefore, the regular expression is a closure. Because after Q0, you have transition to Q1 and Q2. From Q1 and Q2, we will never be able to reach back to Q0, the final state. And therefore, a closure is the regular expression. It is not a closure, be a closure, because Q2 is not the final state. Is it clear? If it's clear, you can raise the hands, or else you have to say repeat in the box. Okay. The rest. Okay. So this is how you try to identify. Hope you have understood. Thank you for your responses, ma'am. Hope you have understood. This is how you try to represent the right quotient of two given languages. Now the next question is, we have learned that you have a regular language, and we also know there is various combinations of it, right linear, left linear, and we also have linear language. Now tell me, there are certain languages which cannot be considered as a regular language. So we'll have two or three options. Tell me whether they are regular or they are not regular. And then we'll move on to the next one. Now I'll post one, A closure or B closure. Tell me whether it is regular or not regular. If it is regular, in the chat box you can write it as RE. If it is not regular, you will put it as not. A closure, B closure is a regular language, or is it not a regular language? Okay. Okay, you find out it's a regular language. Fine. Now, I have A per N and B per N. You have another language here. A per N and B per N. Tell me whether it is regular or not. You A closure, B closure is regular. Tell me A per N, B per N, whether it's it regular or not. If it's regular, put it as RE, else it is not, NOT. Okay. How many of you say it's a regular language? Should I again have an okay? You have only two options. Either it is regular or it is not regular. It is not regular, okay. Okay. Now the reason for the given language not being regular is simply because you cannot keep an count of A and then say if there is four occurrences of A, You are supposed to have only four occurrences of B. In our finite automata, you know from if on Q naught, if the next state is A, if the next character is A, you know where to move, where not to move. That is all. We never that finite automata never keeps into account or keeps a track of the things which has happened in the past. It doesn't have a memory as such, and therefore it is not an regular expression. Fine. Now tell me where A per n B is in regular language or not. A per n followed by B, is it a regular language or is it not a regular language? We have polls. You can give your responses through the poll. A per n B, is it regular or is it not regular? Okay, I'll end the poll. And many of you have said it is not regular, but I'll say it is regular language. Now, why is it regular? For A per n, B per n, we will not be able to write an regular expression. Okay, but for A per n, B, we'll be able to write an regular expression. If n is greater than zero, greater than or equal to zero, we'll make it as A closure B. In case if n is greater than or equal to one, we'll say n positive closure B, right? We'll have it as A closure B. If n is greater than or equal to 2, I can put it as A, two A's, and then an A closure B. Fine. So now what happens? You can represent A per n B in terms of a regular expression, whereas A per n B power n cannot be considered in this way. I'll tell you the only option to represent, sorry, the only way to represent A per n B per n is A closure B closure. The only way you can represent A per n, B per n is A closure, B closure. But why does it fail? It fails because when you say A closure, B closure, it is the sequence is followed. You'll have a sequence of A followed by a sequence of B. But the number of occurrences of A cannot be matched with the number of occurrences of B, and therefore it is not a regular language, whereas A per n B is a regular language. Now tell me, have you understood this concept? If you have understood it, you can raise your hands. We'll move forward. Okay. Now, how do I identify that a given language is non-regular? You have to prove there are certain set of languages which are existing, which are non-regular, and that is the reason why we move on to another set of specification, which you call it as a context-free language, and which is represented by context-free grammar. And with that in mind, we'll just find out why it is why do we have a set of non-regular languages and how do I represent it? Now if you just see here, the regular languages, A closure B is regular, A closure C plus A is regular, and so on and so forth. We have a lot of representations over there. But then if I have some balanced constructs saying the number of A has to be equal to the number of B, then it comes into in terms of a non-regular language. And the next example what you have is B VR. What is VVR? You take a string, whatever I have in the first half has to be reversed in the second half. And that is what you represent it is by VV reverse. Now that can also not be accommodated because there is no way I could have the characters which I read in the first half of the string to be stored, and therefore it is a non-regular language. Now the question is, how do I identify it? And for which, how do I prove that a language is not regular? Or the other way around, how do I prove that there is that I cannot draw an finite automata, let it be deterministic or non-deterministic? Or I should prove that I cannot write a regular expression, or the other way around is I should prove that I cannot write it in terms of a regular grammar. So how can I prove that a language is regular or how a language is not regular? And the only option is something called as pumping lemma. Now what happens here, they call it as a pigeonhole principle, and they say that you have three pigeonholes where every hole can accommodate only one pigeon. So if there is one more in addition, that has to be accommodated somewhere within it, which is impossible based on the theory. A pigeonhole has to contain at least two pigeons to accommodate all four in the three boxes. So what happens is you have the pigeonhole principle. Now pigeonhole principle is used in the pumping lemma concept. So how do I do it? There are n pigeons and m pigeonholes. N has to be greater than m, and though it has to be accommodated in the m pigeonholes. So any number of pigeons we add, you should be in a position to accommodate within the pigeonholes. That is where you can have the condition. Now, the pumping lemma. We'll go directly to the pumping lemma where we'll try to understand how it works. If a language L is accepted by an deterministic finite automata with M states, let it there be any number of states. Okay, then we'll take a string X where the length of the string X has to be greater than the number of states. That is what this line means. The length of the string X has to be greater than the number of states M, and the string X can be divided into three substrings U, V, and W. Fine. So what have we done? The first point is a language L is accepted by a DFA. Now this DFA has M states, second point, and we'll take any string X which is represented by the DFA, and the length of the string has to be greater than the number of states. That is your third point. The number of string length of the string has to be greater than the number of states. And if this condition is satisfied, you divide X into three different substrings U, V, and W, such that you only concentrate on the V part, the middle part. Okay. V should not be equivalent to an empty string, which means we should at least have one character. V should not be equivalent to empty string, which means we should at least have one character. And you take uv closure w, you take any substring by populating v n number of times, it should be a part of the given string in L, or it should satisfy the condition of L. With this information, we'll try to understand the first problem, come back again and revisit, just to have a clear understanding of what pumping lemma is. Now we'll just we'll do it one by one. Okay, let me delete it for our understanding. Okay, now you have a language a per n, b per n, which we have already told that it is not a regular language. Okay, having said that, n is greater than or equal to 0. We'll take a string a, b, b, for example. Now, what should I do? Let this u, v talk of, consider, you have to define something. You have to define what is u, what is v, and what is w. Let this uv represent a per n. Okay, let this uv represent a per n, and let v w represent b per n. W, let it represent B per N. Now what happens? U, V, W put together is A per N, B per N. Okay, U, V, W put together, it is A per N, B per N. Now what am I supposed to do? We have to split V in such a way V is not an empty string. So let me take in a UV, let me take V to be, we'll do some modifications here. Let me take V to be A per X. Instead of N, I am replacing it with X, where X would be less than N. Okay, and then I'll explain this with another example. Now what should I do? According to this example, what I have to do is you have to populate V, and for every of V population, it has to satisfy A per N, B per N. That is all what it means. For every of the populating part, it has to satisfy A per N, B per N. Fine. Now we'll take an example. We'll take with 3 A's and 2 B's. Okay, this is just for our understanding. This is an example where we'll try to replace every other thing. So what is UVW? UVW is 3A and 3B's. What is UV? UV represent only 3A's. Okay, what about W? W represents 3B's. Now what does V mean? Let me take V to be a single A. If V is a single A, what is U? U becomes 2A. Fine. Now what am I supposed to do? You have to populate this part. So if I substitute U, V and W here, what is U? U is 2A. What is V? V is a single A. And what is W? W is 3A's. Right? Now what am I supposed to do? This I has to be populated from 0, 1, 2 and 3. So if I is populated, okay, if in case I is populated, what happens when I say you have this to be 0, I becomes 0 now. If I is 0, what is the string which will be generated? You'll have 2 A's with 3 B's. Okay, and if I is 1, what string will it be generated? When I becomes 1, I becomes 1, the string generated is 3 A's with 3 B's. Okay, when I becomes 2, the string generated would be 4 A's and 3 B's. Now what happens? Only when I is 1, the condition is satisfied. The number of A is equal to the number of B. And when I is 0 or I is 2 or I to be any number, the condition will not be satisfied. Now, for how do I do it? And I, for any value of I, the condition A per N, B per N has to be satisfied. If it cannot be, then it is not a regular language. Fine. So that is how it all works. So I'll repeat. You take a language L, any language where you have M states, and then you take a string, try to divide them into 3 substrings, U, V and W, and then U, V closure, you populate V part alone n number of times. Even it is populated any number of times, the string what is generated should satisfy the language constraint. If not, it is not a regular language. Fine. How many of you have understood this part? Should I repeat?
Repeat, ma'am.
Okay. Yes, ma'am. Repeat ka. Understood. Okay. Okay, ma'am. Okay. Now we'll go step by step. As and when I try to write something, just let me know whether you have understood or you haven't understood. Okay, this is just for our clarity purpose. You take for We'll just try to understand this example alone, and then we'll try to map it with the given definition. uh, Madhu ma'am, students, please ensure that you have understood the concept. Okay, else you can also post it onto the chat box. Now you have a per n, b per n. What should I do is to take any string. The easy way of taking it is I'll take any string that is 3a. This is a string x. Okay. Now this string x has to be divided into three substrings. It need not be equal substrings. It can be put into any substring. So let me take uv as a and w as 3b's. Okay. Now I have divided them into two. This uv I'll again divide it. So what I'll do is I'll take it to be 2a's and b I'll take it to be a single a. Now, according to the pumping lemma, these alone, the substring V alone has to be populated n times or has to be populated any number of times. And any number of times it gets populated, it has to be a part of the given definition. So, how do I do it? The other way of writing it is UVW, V alone will be populated. Okay. UVW where V alone will be populated any number of times. So instead of UVW, what can I substitute now? What is U? U is, instead of U, I'll replace it by 2A's. Instead of V, I'll replace it by a single A. Instead of W, I'll replace it by 3B's. Now what happens? I has to be populated. If I is 0, you will have a per 0 with 3 b's. What is a per 0? A per 0 is lambda. So you will have 2 a's with 3 b's. What about I equal to 1? When I is 1, it is a per 1 with b. So what happens? A occurs only once. So the condition is satisfied. You will have equal number of a and b. When I is 2, the number of a will be more than the number of b's. Now you populate I any number of times, the number of A will be greater than the number of B, and hence A per n, B per n cannot be satisfied, because this, for any value of I, A per n, B per n has to be satisfied. That is the requirement. And we prove that for only for I equal to 1, A per n, B per n is satisfied. For the rest of the values, the condition is not satisfied, and therefore it is not an regular language. Now, how many of you have understood it? Okay. Okay. So now that is what this pumping lemma says. You divide the x into three strings. V should not be an empty string. That is a mandate. And you populate V, and when you populate it, you will get a string. That string has to satisfy the given language. Fine, it hasn't satisfied. But what about A-B closure? B closure part, I'll take it as W. AA, I'll take it as UV. And then this is the other way of defining it. I have taken it as A per X. V alone, I have taken it as A per X. And then A per N minus X is considered. Now what should I do? I should populate the V part alone. Now the same explanation goes. If it is AA, BB, first time when A is 0, okay, we'll go ahead with this condition. I think this would be more, we'll duplicate it. And we'll do it for A closure, B closure. Okay, we'll not talk about this part. So when I is 0, we have taken the same explanation. When I is 0, you have a sequence of A followed by a sequence of B. When I is 1, you have a sequence of A followed by a sequence of B. There is no, every number, it is not the constraint on the number of A and B. It is only on sequencing part. And therefore, any number of I value gets generated. It satisfies, it is a part of A closure, B closure. And therefore, A closure, B closure is a regular language. Can I move on to the next example? I'll take one more and then we'll move ahead. Now, how do I generalize it? Okay, any type of problem which is given, the first you will have somewhere a power n or 0 power n or whatever it is, that you take it as uv. Okay, now for here you can take the example of 0, 0, 1, 0, 0. So this 0, 0 put together you take it as uv, and 1, 0, 0 you take it as w. Okay, so now what happens, you can populate v alone and say it is not a part of the language. Fine. So here you have a per n, b per n. Try to understand this problem alone. Wherever you are given something to the power n, that part, the first part, you take it as uv. The rest, you any number of values you have, you take it as w, and then you try to explain it. Fine. We'll stop here. If you have any doubts, you can ask me. The rest, I'll be sharing some solved questions. We'll also upload the